Have you ever wanted to remove an object or several different objects from an image, or even fix a distorted image? Imagine if you could do this by just specifying the object you want to remove, rather than manually selecting the area it covers. That is exactly what our deep learning application aims to do. We combine image and painting with object detection in our product to reconstruct images undetectably. Take this photograph for example. There's way too many people in it. What if we could entirely remove some of them from the image without damaging the quality? Boom. And that's what we're talking about. But what exactly is image in painting and how does it work? Image in painting is a reconstruction technique in which distorted, faded, or absent sections of an image are restored with the intention of portraying the image as it was initially created. Object detection is used to semantically identify objects in an image. We use a region-based convolutional neural network to mask out identified objects in the frame, and the concept of partial convolutions applied to UNet to manipulate those sections of the frame. Our work is a re-implementation of NVIDIA's paper on image in painting, and we extend this by adding object detection to it. Here's how it works. In a typical forward pass through UPaint's architecture, the image is fed to the region-based CNN, which is responsible for detecting objects in the image. It demarcates and classifies the objects detected. Next, the RCNN's output is fed to the next segment of the system, where a UNet model, which utilizes partial convolutions, is used to inpaint the chosen objects in the image. While training our models, we relied on two main datasets. First was NVIDIA's irregular mask dataset, which contains over 50,000 training images and 20,000 test images, structured to include a list of masks and a list of images to reconstruct the images which include those masks. MIT provides the Places 2 dataset, which consists of close to 2 million images. This was ideal to train our convolutional neural networks to be used for scene recognition as well as generic deep scene features for visual recognition. Here are some of the key features of UPaint. The idea behind partial convolution is to apply the convolutional layer to both the input and the mask corresponding to the erased area. By doing so, we shrink the region of the mask filled with zeros after every partial convolution. At the end, the mask is full of ones and the image is fully reconstructed. This technique allows an intuitive reconstruction of the image, starting from the border of the erased area and slowly converging toward its center. UNet is the base architecture upon which most image-to-image synthesis algorithms are built. It consists of a series of downsampling layers followed by upsampling in the shape of a U. Generally, the number of channels doubles in every downsampling layer. The upsampling contains skip connections and the number of channels are halved while passing through each layer. We use a modified version of the UNet model to inpaint our images, which incorporates attention by using the bottleneck layers to extract important features from every skip connection. The first step in this project was to modify the convolutional layers in the network by partial convolutions. This required us to modify the behavior of the skip connections and the way the network processed inputs in UNet's encoding and decoding paths. To do this, we created the partial convolution layer from scratch using TensorFlow. 6 of the losses described in NVIDIA's paper were implemented, and it was interesting to see how they interacted together. We tried modifying each of their coefficients and observed that the per pixel loss and the style loss had the biggest impact on the results, while the total variation and perceptual losses were mostly for fine-tuning. We know that NVIDIA Corporation has trained their network for a week on several powerful GPUs. Therefore, we needed to find clever ways to speed up the process in order to achieve similar results in a reasonable amount of time. Our approach required around 10 days to train our model entirely and get inpainted results equivalent in quality to NVIDIA's publication. With the object detection component, we realized how the capabilities of a CNN can be extended. A typical CNN can only tell you the class of the objects, but not where they are located, but a region-based CNN is capable of detecting the exact location of the objects as well. Lastly, the novelty in our system lies in the inclusion of object detection to supplement the image inpainting component. Our system runs properly from end to end and we are proud of it.